One of the assumptions of fitting a linear model is that the independent variables involved in the model are supposed to be uncorrelated. When this assumption is violated, we say that there is multicollinearity present. In this module, we will look at the consequences of such violation of the assumption. In this current module, we will discuss the presence of multicollinearity in a data set and its consequences. Originally, multicollinearity meant the existence of a perfect or exact linear relationship among some or all of the explanatory variables of a regression model. Hence, if x1, x2, xk are the k explanatory variables, then we can write a linear combination of them, that is lambda 1 x1 plus lambda 2 x2 plus lambda k xk equals 0, where lambda 1, 2, k are k constants such that not all of them are 0 at the same time. However, in recent times, multicollinearity is used in a broader sense to include the case of perfect multicollinearity as shown in the above equation, as well as the case where x variables are intercorrelated but not perfectly so, which can be written as follows. We can write a linear combination of the explanatory variables x1, x2, xk, and in addition we have a stochastic error term vi. Thus, the linear combination can be written as lambda 1 x1 plus lambda 2 x2 plus lambda k xk plus vi equals 0. Now, looking at the definitions of the nature of multicollinearity present in a dataset, we can either have perfect multicollinearity or partial multicollinearity. Let us look at both the cases in detail. When two or more explanatory variables overlap completely, where one variable is a perfect linear function of the other, such that the method of analysis cannot distinguish one explanatory variable from the other, then we say there is presence of perfect multicollinearity. This condition will prevent a multiple regression from estimating the coefficients. The equation for obtaining the estimates of the regression coefficient then becomes unsolvable. This condition is sometimes also referred to as full multicollinearity. In case of partial multicollinearity, when two or more explanatory variables overlap such that they are correlated with each other, but they still contain independent variation. In other words, when not all the explanatory variables are perfect linear combinations of each other, we say that there is presence of partial multicollinearity. This condition limits the extent to which analysis can distinguish the causal importance of one explanatory variable from another. That is, it becomes increasingly difficult to single out the variables that are most significant in describing the regression model. Let us look at an example of multicollinearity. Suppose we have a data set that contains three explanatory variables x1, x2 and x3, such that x1 takes the values 10, 15, 18, 24 and 30. x2 takes the value 50, 75, 90, 120 and 150. However, the third variable x3 takes the value 52, 75, 97, 129 and 152. Considering this data as a numerical example of the presence of multicollinearity, it is apparent that x2, the second explanatory variable, can be written as 5 times x1. Therefore, there is perfect collinearity between x1 and x2. But the variable x3, which was also created from x1 by simply adding the following numbers which were taken from the random number table, the numbers being 2, 0, 7, 9 and 2, is said to have partial multicollinearity with x1, where x3 can be written as 5 times x1 plus the numbers taken from the random number table. For example, the first value of x3 is 5 times x1 plus 2, which gives us 52. The second value is 5 times x1, which is 15, plus 0. The third value is 5 times the value of x1 plus 7, and so on. Now, there is no perfect collinearity between x1 and x3. However, the two variables are highly correlated, and this can be seen from calculating the correlation coefficient between x1 and x3, which turns out to be 0.9958. Now, using R, we can calculate correlation coefficient. We have discussed this earlier, but I will do a quick recap of how to obtain the correlation coefficient between two variables. First, we enter the values of the three variables, x1, x2 and x3. We are interested here to look at the correlation coefficient between x1 and x3. Hence, we use the COR function in R and use x1 and x3 as the two variables, and the R output 0.995817 is the output that R gives us, the correlation coefficient between x1 and x3. If multicollinearity is perfect, the regression coefficients of the x variables are indeterminate and their standard errors are infinite. If the multicollinearity is less than perfect, in other words, if there is partial multicollinearity, the standard errors are large, corresponding to the estimates of the regression coefficient, which means the coefficient cannot be estimated with great precision or accuracy. Now, interpreting multicollinearity in terms of the regression coefficients. If we recall the meaning of correlation coefficient beta 1, it gives us the rate of change in the average value of dependent variable y as the independent variable or explanatory variable x1 changes by a unit, holding the other explanatory variable x2 as constant. But if x1 and x2 are perfectly collinear, there is no way x2 can be kept fixed. What it means is that as x1 changes, so does x2 by a constant factor. Thus, there is no way of disentangling the separate influences of the two variables from the given sample. In applied econometrics, this condition is most damaging, since the entire idea is to separate the partial effects of both the explanatory variables x1 and x2 from each other. But in case of multicollinearity being present in the dataset, we are unable to do so. Hence, learning about the theoretical and practical consequences of multicollinearity is of utmost importance. Let us first look at the theoretical consequences of multicollinearity. Let us look at the problem multicollinearity poses in the mathematics involved in obtaining the estimates of the regression coefficients. First of all, it is true that even in the case of near multicollinearity, the ordinary least square estimator are unbiased. But unbiasedness is a multi-sample or repeated sampling property. What it means is that keeping the value of x variables fixed, if we obtain repeated sample and for each sample we compute the ordinary least square estimates for each of these samples, average value of the estimates of the parameters obtained for each sample will converge to the true population value of the estimator as the number of samples increase. The second theoretical consequence of multicollinearity is that it is also true that collinearity does not destroy the property of minimum variance. In the class of all linear unbiased estimators, the ordinary least square estimators have minimum variance. That is, they are the most efficient. But this does not mean that the variance of an OLS estimator will necessarily be a small number in any given sample. Third, multicollinearity is essentially a sample phenomena in the sense that even if the X variables are not linearly related in the population scenario, they may be so related in the particular sample at hand. When we postulate the theoretical or population regression function, we believe that all the X variables included in the model have a separate or independent influence on dependent variable Y. That is, the effect of one explanatory variable does not depend or is not related to the influence of another explanatory variable on our dependent variable Y. But it may happen that in any given sample that is used to test the population regression function, some or all of the X are so highly collinear that we cannot isolate one individual explanatory variable from the other. Let us illustrate the theoretical consequences of multicollinearity using an example. Consider the consumption, expenditure, and income example, where consumption expenditure is the response and income is the predictor variable or the explanatory variable. Economists believe that besides income, the wealth of the consumer is also an important explanatory variable to determine the consumption expenditure of an individual. Thus, using wealth and income as explanatory variables, we can write the regression model as consumption expenditure equals beta 1 plus beta 2 income plus beta 3 wealth plus epsilon I, where beta 1, beta 2 and beta 3 are the three regression coefficients. Now it may so happen that when we obtain data on income and wealth, the data may be highly, if not perfectly, collinear. Wealthier people tend to have higher income. Thus, although in theory, income and wealth are logical candidates to explain the behavior of consumption expenditure of an individual, in practice it may be difficult to disentangle the separate influences of income and wealth on consumption expenditure of an individual. Now let us look at a number of practical consequences of multicollinearity. We will see that in practice, multicollinearity has more serious consequences than we think. Although best linear unbiased estimator or BLUE, the ordinary least square estimators of the regression coefficients have large variances and covariances, making precise estimation difficult. Second, because of the above consequence, the confidence intervals tend to be much wider, leading to the acceptance of the zero null hypothesis more readily. Also, because of the first consequence, the t ratio of one or more coefficient tends to be statistically insignificant. Although the t ratio of one or more coefficient is statistically insignificant, R square, which is the overall measure of goodness of fit of the model, can be very high. The ordinary least square estimators and their standard errors can be sensitive to small changes in the data. Now let us look at each of these practical consequences of multicollinearity in detail. First, let us illustrate the practical consequences of multicollinearity. Large variances of OLS estimators of regression coefficients. Suppose that the regression line is given by yi equals beta naught plus beta 1 x1I plus beta 2 x2I plus epsilon I. If we estimate the regression coefficient by the methods of ordinary least square, then the variances and covariances of the estimates are given by the following expressions. Variance of beta 1 hat, where beta 1 hat is the estimate of the regression coefficient corresponding to x1, is given by sigma square divided by sum of x1I square times 1 minus r12 square. Variance of beta 2 hat, where beta 2 hat is the estimate of the regression coefficient corresponding to x2, is given by sigma square divided by sum of x2I square times 1 minus r12 square, where r12 square is the correlation coefficient between x1 and x2. And covariance between beta 1 hat and beta 2 hat is given by negative r12 times sigma square divided by 1 minus r square 12 times square root of sum of x1I square times sum of x2I square. Now it is apparent from the expressions of variances and covariances between the two regression coefficients that the variance of the two estimators increase, and in the limit when r12 equals 1, they are infinite. It is equally clear that as r12 increases towards 1, the covariance of the two estimators also increases in absolute value. As we can see from the expressions, in the denominators, in both variances and covariance, we have 1 minus r12 square. Thus, as I have just mentioned, as the value of r1 tends to 1, 1 minus r12 square tends to 0 in the denominator. Thus, variances and covariance between the regression coefficient estimates tends to infinite values with the increase in r12. The speed with which the variances and covariance increase can be determined, and we determine it using the variance inflation factor or VIF. The VIF is given by 1 divided by 1 minus r12 square. VIF shows how the variance of an estimator is inflated by the presence of multicollinearity. As r12 approaches 1, the VIF approaches infinity. As we can readily see, if there is no collinearity between the explanatory variables, that is, if r12 is very close to 0, then variance inflation factor or VIF will become 1. Now, let us illustrate the practical consequence of multicollinearity, where we have wider confidence intervals as a result of presence of multicollinearity. Because of the large standard errors of the regression coefficients, the confidence intervals tend to be larger. For example, suppose we have the correlation coefficient between x1 and x2 take the value 0.95, which is very close to 1. Hence, it means that x1 and x2 are highly collinear. And comparing it with r12 equals 0, where x1 and x2 are not related at all, then the confidence interval for beta 1 is larger in case of r12 equals 0.95 than when r12 equals 0 by a factor square root of 10.26. Thus, in case of high multicollinearity, the sample data may give rise to such a wide confidence interval such that a lot of false hypotheses might be accepted. Now, moving on to the next consequence of multicollinearity, that is insignificant t-ratios. Now, to test the null hypothesis that an individual regression coefficient, say beta 1 hat equals 0, we use the t-test statistic, which is given by beta 1 hat divided by standard error of beta 1 hat divided by square root of sample size n, and compare the estimated t-value with the critical t-value from the t-distribution table. But as we have discussed before, in the presence of high collinearity, the standard errors of the regressions increase manifold and thus makes the t-values very, very small. Thus, in turn, prompts us to increasingly accept the null hypothesis that the true value is 0. And the next practical consequence of multicollinearity is that the high values of R square but very few significant t ratios. Let us consider the linear regression model yi equals beta naught plus beta 1 x1i plus beta 2 x2i plus beta k xki plus epsilon I. In cases of high collinearity, it is possible to find that one or more of the partial slope coefficients are individually statistically insignificant based on the t-test. However, the R square in such situation may be so high that on the basis of the f-test, one can convincingly reject the hypothesis that jointly the regression coefficients beta 1 equals beta 2 equals beta k equals 0. This is actually a strong signal of the presence of multicollinearity. In other words, if we fit a regression model and we see that individually the regression coefficients are insignificant, however, looking at the R square, we can see that the overall fit of the model is good, then we know that there is presence of multicollinearity in the dataset. Now let us look at the final practical consequence of presence of multicollinearity in a dataset. The sensitivity of ordinary least square estimators and their standard errors due to small changes in data can be seen through illustration using the next couple of datasets as examples. We can see that as long as multicollinearity is not perfect, estimation of the regression coefficient is possible. Hence, it does not indicate the presence of multicollinearity unless we look deeper. However, the estimates and their standard errors become very sensitive to even the slightest change in the dataset, which again is evidence of multicollinearity. In order to demonstrate this fact, let us first consider two sets of data as follow. In each of these datasets, we have a y variable, which is the dependent variable, and we have two explanatory variables x1 and x2 in each case. We use these two datasets and using the LM function in R, we fit two separate regression models to the datasets. Here is the R code. We first enter the data corresponding to the three variables y, x1 and x2. Then we put them in a data frame, and using this dataset, we fit the regression model of y over x1 and x2 using the LM function in R. After fitting the model, we look at the summary of the linear model that we have just fitted, and R gives us the estimates of the intercept and the regression coefficient corresponding to the two explanatory variables x1 and x2 along with their standard errors and the corresponding p-values to test the significance of each regression coefficient. On the next slide, we see the R code and output of fitting the second regression model to the second dataset using the same steps as before, and we look at the summary of the now fitted regression model, which gives us the estimates, standard errors, and the p-values corresponding to each regression coefficient, including the intercept. Now, from the R output of fitting the first regression model, we can clearly see that none of the regression coefficients are individually significant at the conventional 1% or 5% levels of significance alpha. Although we can see that beta 1 hat is significant at the 10% level on the basis of a one-tailed t-test. Now consider the second dataset. The only difference between the first and the second dataset is that the third and fourth values of explanatory variable x2 are interchanged in the second dataset. We again fit a linear regression model to this dataset using the LM function in R, and we have already looked at the R code and R output. We can see that due to a slight change in the data, beta 1 hat, which was statistically significant in the first dataset before at the 10% level of significance, is no longer significant at that level. Also, in case of the first model, the covariance between the estimates of regression coefficients is negative 0.003449, and in the second model, it is given by negative 0.011339, which is almost 3 times the covariance in the first case. All these changes may be attributed to increased multicollinearity. The correlation coefficient between the two explanatory variables have also increased from 0.5523 to 0.8285. This increase is direct evidence of multicollinearity present in the dataset. Let us illustrate the points that we have so far discussed using the consumption expenditure and income wealth dataset. To illustrate the points, let us consider a data on consumption expenditure, which is our dependent variable, and income and wealth of individuals are the two independent variables. In the following table, we have the data corresponding to Y, X1 and X2. Now let us look at the R code to fit a linear regression model of Y on X1 and X2. We use the same code as we have used before for the two datasets, and we look at the summary of the model that we have fitted using the LM function in R. In the summary, we are presented with the estimates of the intercept parameter and the two regression coefficients along with their standard errors and the corresponding p-values for each of the regression coefficients. The regression output from R using the consumption expenditure and income dataset shows that the multiple correlation coefficient R square takes the value 0.9635. From the definition of R square, we know that it explains the amount of variability in response that is explained by the explanatory variables. Hence, the variable income and wealth explain about 96.35% of variation in consumption expenditure. Yet, if we look at the coefficients, neither of the slope coefficient corresponding to income or wealth are individually statistically significant. Moreover, not only do we see that the wealth variable is insignificant, but also has the wrong sign. We know that wealthier people tend to spend more on consumable items. Hence, consumption expenditure should have a positive correlation with wealth. However, the coefficient estimate corresponding to wealth in the R output is shown as negative 0.04243. However, intuitively thinking, this should not be the case. Now, although we see that individually the variables income and wealth are insignificant, but the overall F statistic, which is also shown in the R output to test the significance of the entire model, takes the value 92.4, which is highly significant. Thus, testing the null hypothesis H naught such that beta naught equals beta 1 equals beta 2 equals 0 is rejected. Therefore, individually, we can accept the null hypothesis that the two partial slopes are 0, but when testing the overall model, the above null hypothesis cannot be accepted. Our example demonstrates what dramatic effects multicollinearity can have on regression model. The fact the above conclusions are drawn from the output of fitting the model, it means that the two variables income and wealth are so highly correlated that it is impossible to isolate the individual impact of either of them. Now, as a fact, we can further illustrate multicollinearity by regressing x1 on x2. When we regress x1 on x2 using R, we get the following R output, in which case the R square or the multiple correlation between the two variables is 0.9979, which shows that almost all of the variability in x1, which is income, can be explained by the other explanatory variable x2, which is wealth. Now, next what we do is we regress consumption expenditure, which is our y, on income and wealth separately. And we see that in each case, the explanatory variable is significant. The R output from the two model fitting are shown in the next slide, and one look at the R squares corresponding to each model is evidence of high correlation between consumption expenditure and income, and consumption expenditure and wealth separately. Regression models of y on the two explanatory variables income and wealth separately show that clearly in situations of extreme multicollinearity, dropping the highly collinear variables oftentimes makes the other x variables statistically significant. Now, when we have multicollinearity present in data, there are several methods of detecting the presence of multicollinearity and several remedial measures to remove multicollinearity from a dataset. But in order to do that, we will dedicate separate modules for remedial measures and detection of multicollinearity in a dataset. In this module, we have learned the different consequences of the presence of multicollinearity. When we have several independent variables and there is either a perfect or near perfect linear relationship between them, then we say that multicollinearity is present. And if multicollinearity is not taken care of, then ignoring multicollinearity results in different types of faulty inference and faulty estimates of the regression parameters. We have discussed what are the consequences of such multicollinearity present in the dataset.